Welcome to the HT8 MCU Basic Tutorial, Comprehensive Experiment 2, LED Brightness Adjustment. This experiment will be explained from the following 5 aspects, which are LED Brightness Adjustment Experiment Introduction, Hardware Connections, Program Development, Practice Results, and Experiment Summary. LED Brightness Adjustment Experiment Introduction. The learning objectives of this experiment are to master the ADC functions, as well as the timer, counter, and PWM modes of the timer module. Let's take a look at the experimental content. Use the upper and lower ends of a potentiometer to form a voltage divider circuit, and connect the output voltage to an ADC pin. The MCU determines the LED brightness level after ADC sampling. Use a timer in the timer, counter mode to control the I/O port to time-sharing drive the digital tube. Use a timer in the PWM mode to modify the PWM duty cycle according to the brightness level, thereby adjusting the LED brightness. The following table shows the division of LED brightness levels in this experiment, which are divided into 4 levels based on different sampling voltage levels, with duty cycles of 0%, 10%, 50%, and 100% respectively. In this experiment, in addition to the timer, the GPIO, ADC, internal oscillator and watchdog functions are also used. Before moving on, we need to review some PWM signal knowledge points. There are 2 crucial parameters in PWM, which are frequency and duty cycle. Frequency refers to the number of pulse signals within 1 second, usually measured in hertz, and period is the inverse of frequency. The PWM frequency for this experiment is 2 kHz, so the period is 0.5 milliseconds. Duty cycle refers to the percentage of the active level duration in a pulse period over the whole pulse period. The higher the duty cycle, the longer the active level duration within a cycle, resulting in greater LED brightness. Here are the materials required for this experiment. This experiment uses the DEV3195 development board as the main control board. Uses the emulator to provide a 5 volts power supply voltage, which can be used together with an LED, a 1-digit digital tube, a potentiometer, a capacitor, several resistors, a breadboard, Type-C, and connection lines. Hardware connections. This section introduces the schematic diagram of the experiment. The DEV3195 board uses the HT66V3195 as its main control MCU. There is a bypass capacitor between the power and ground on the board, which is used to stabilize the power supply and filter out AC noise. By rotating the sliding end of the potentiometer, the output voltage on the middle pin of the potentiometer is changed. The output voltage is then connected to the ADC pin after passing through the RC filter circuit. The MCU calculates the LED brightness level based on the ADC sampling value. Connect the positive terminal of the LED to the PWM output pin, and connect the negative terminal in series with a current limiting resistor to ground. A common anode digital tube is used to display the LED brightness level on the digital tube. This experiment is conducted using a breadboard. The following is the connection diagram of the experiment. The power supply is provided by the E-Link Pro 2, with a voltage of approximately 5 volts. The top of the development board is the code programming pin, which can be emulated or programmed using the E-Link Pro 2 or eWriter Pro 2. The following is the breadboard wiring physical diagram, provided for your reference. Program development. Let's first take a look at the main function flow of the MCU, which includes the system clock configuration, watchdog configuration, digital tube I/O configuration and initialization, timer configuration, ADC configuration, enable global interrupt, clearing watchdog, ADC sampling, LED brightness adjustment, and digital tube display. Next, look at the timer module interrupt function flow. When the MCU is woken up, the timer will be enabled, and a timer interrupt will be entered after an interval of 2 milliseconds. This interrupt uses the timer, counter function, and comparator match. Therefore, the interrupt request flag bit STMAF should be checked after entering the interrupt. When the timer interrupt is serviced, the display flag is set to 1 and the segment count value is increased by 1. After the main function detects the display flag, it selects which segment to light up according to the segment count value. Now, let's go through the program example. This is the main.c file. The experiment includes 2 header files. One is the HT66F3195.h header file, which mainly defines and declares the registers, ports, peripherals, etc. of the HT66F3195 and HT66V3195 microcontrollers, facilitating subsequent program development. The other is stdlib.h header file, which provides functions related to numerical conversion, etc., and is required when processing ADC data. Before writing a program, macro definitions are generally used to define the pins to be used, so as to facilitate the writing of the program. Here are respectively the macro definitions of the digital tube pins: digital tube pin output configuration, digital tube pin low output command, digital tube pin high output command. The following is the display encoding table of the common anode digital tube. The MCU controls the digital tube I/O ports to display the corresponding digits using the lookup table. The combined use of structs and unions can make program organization clearer and more efficient. The following defines a struct and a union for storing the data displayed by the digital tube. Function declaration. It notifies the compiler of the function names, return value types and parameter list, resolving compilation errors caused by the function being defined after it is called. Variable declaration and definition. It aims to create variables and notify the compiler of the variable names and data type, and allocate memory for them. The following is the main function. First, initialize the variables. Here, some variables are not initialized to 0, so that the MCU can complete an ADC sampling and adjust the LED brightness after power on. Then configure the system clock, watchdog, digital tube I/O port, timer, and ADC, and enable the global interrupt. After the MCU configuration is completed, it enters the main loop. In the main loop, the watchdog is cleared to prevent the MCU from resetting, and then the ADC sampling is executed and the LED brightness level is calculated. When the LED brightness level differs from the current level and the change in ADC value between the previous and current samplings exceeds 40, the MCU modifies the PWM duty cycle to adjust the LED brightness. The LED brightness level is only updated when the difference between the newly sampled ADC value and the previous one exceeds 40, which can effectively avoid frequent changes in the LED brightness level when the critical value is sampled. The digital tube uses a time-sharing driving segment method, displaying only one segment at a time and switching segment every 2 milliseconds. The following is an introduction of various parts of the main function. The first is the system clock configuration function. which uses an internal oscillator and selects the 8 MHz clock. The watchdog configuration function enables the watchdog and sets the timeout period to 512 milliseconds. Once the watchdog times out, the MCU will reset, therefore it is necessary to clear watchdog strategically during the main loop. In the digital tube I/O configuration function, set the digital tube I/O port to output mode and control the I/O port to turn off the digital tube according to the characteristics of the common anode digital tube. Since the digital tube is a common anode digital tube, setting the segment port to a high level will turn off the digital tube. This is the STM timer configuration function. First, set the timer operating in the timer, counter mode, and select the system clock divided by 4 as the timer clock. Then select comparator A match as the timer counter clear condition. When the counter value matches the preset value in comparator A, the comparator A match interrupt request flag will be generated. The count value of comparator A is set as 4000. Since the timer clock is 2 MHz, the corresponding counting time is 2 milliseconds. Clear the multifunction interrupt 0 request flag and enable the multifunction interrupt. Clear the comparator A match interrupt request flag and enable comparator A match interrupt. Finally, enable the timer. This is the PTM timer configuration function. Set the PD0 pin as the PTP pin function for PWM signal output. Select the system clock divided by 4 as the timer clock. Set the timer operating in the PWM output mode and enable the PTP pin to output in the PWM mode. Select the PTP pin output as active high. Set the PTMAL and PTMAH registers to 0, corresponding to a CCRA count value of 0. Set the PTMRPL and PTMRPH registers to 1000, corresponding to a CCRP count value of 1000. Let's explain the PWM signal. The PWM period equals the CCRP count value divided by the timer clock, which is 0.5 milliseconds. The PWM frequency is the inverse of the PWM period, which is 2 kHz. The PWM duty cycle equals the CCRA count value divided by the CCRP count value, which is 0%. After the configuration is completed, start the timer. Here is the ADC configuration function. Set the PA4 pin to ADC input channel 3, select the system clock divided by 4 as the ADC clock, enable the ADC, and select the external analog input channel as the ADC input. After that, the ADC analog input channel is selected as channel 3, the ADC output data is right aligned, and the reference voltage is selected to be AVDD. This is the ADC sampling function. First, declare some variables used in this function, and then start the ADC sampling. Select the method of continuously measuring 4 times and taking the average for filtering. At the end of each sampling, the ADC value is read from the register and accumulated. After 4 consecutive sampling operations, the ADC sampling is completed and the average sampling value is calculated. Here is the LED brightness adjustment function. The LED brightness adjustment is implemented by adjusting the PWM duty cycle according to the LED brightness level. The PWM duty cycle corresponds to 4 brightness levels, namely 0, 10%, 50%, and 100%. Here is the digital tube display function. The segments are driven in a time-sharing method. Each time, only one segment is driven, and the remaining segments output a high level to turn off the segment. The seg-CNT value ranging from 1 to 7 corresponds respectively to the display of segments A to G on the digital tube, and the remaining segments output a high level. For example, When the seg CNT is equal to 1, at this time, execute an AND operation with the lookup table data and hex FE. This preserves the least significant bit of the data, with all other bits set to 1. Consequently, only segment A is controlled, and the remaining segments output a high level. Finally, the STM timer interrupt function. After entering the timer interrupt, first check the comparator match interrupt request flag, and clear it to 0 via the software, so that this interrupt can be entered next time. Then increment the SEG count value, and set the display flag to 1. After the MCU detects the display flag in the main function, it selects which segment to light up according to the SEG count value. Practice results. After the MCU is powered on, a display of 0 on the digital tube indicates that the current LED is off. The value on the digital tube represents the LED brightness level. When rotating the potentiometer, it can be observed that as the displayed value increases, the LED becomes brighter. Conversely, as the displayed value decreases, the LED becomes dimmer. Experiment summary. This comprehensive experiment uses multiple peripheral functions of the HT8 MCU, including ADC, timer, GPIO, internal oscillator, and watchdog. The hardware circuit includes a voltage divider circuit, an ADC filter circuit, a digital tube driver circuit, and an LED driver circuit. Software processing ADC data can enhance the reliability of ADC functions, including filtering and error elimination. By modifying the PWM duty cycle via software, the LED brightness is adjusted, and the GPIO is controlled to drive the digital tube display. Holtec has a professional service team to assist in development design and after-sales service. Please feel free to contact our business departments for more detailed product information and consultation services.